Welcome to the deep dive. We've got something really foundational today, haven't we?
We really do. It's Louis de Broglie's 1929 Nobel lecture called The Wave Nature of the Electron.
And this isn't just, some dusty old document. It's de Broglie explaining the idea that totally flipped physics on its head. The idea that everything has a wave-like nature.
Exactly. And it's great because he sets the scene himself. He mentions coming back to physics around 1920, really drawn in by this deep mystery enshrouding the structure of matter and the structure of radiations.
And a big part of that mystery was Planck's quantum idea from 1900, right?
That was central. Because before that, physics was kind of broken. It had split into these two camps that just couldn't agree.
Particles on one side, waves on the other, totally incompatible.
Right. And de Broglie's genius, what this lecture is all about, was figuring out how to bring them together.
So our mission today is basically to follow that story, understand the mess physics was in, see how this weird light duality thing cropped up, and then get to de Broglie's big leap.
That's the plan. How he said, look, if light can be two things at once, maybe matter can too. And crucially, how experiments proved him right.
Okay, let's unpack this. So before 1900, things seemed, simpler maybe. You had matter physics. That was all about corpuscles.
Yeah, tiny solid bits, like J.G. Thomson's idea of the electricity corpuscle, what we sort of think of as the electron now.
And these little bits, they just followed Newton's laws. Predictable. A goes here, hits B, B goes there.
Clockwork universe almost.
Yeah.
Then, completely separate, you had radiation physics. Light, basically.
And that was all waves. Young, Fresnel. They'd convinced everyone light was a wave, rippling through this thing called the light ether.
Definitely. And they were absolutely against any idea that light itself could be lumpy or particle-like. No way. Light was smooth, continuous.
Okay, so two distinct worlds. Particles behaving nicely, waves behaving nicely. But what happens when they interact? Like when matter absorbs or emits light?
That's where it all went wrong. They just couldn't make the two systems mesh. The math didn't work.
The source calls the attempts imprecise and even inadmissible conclusions. Sounds pretty bad.
It was worse than bad. The biggest problem, the most glaring failure, was this prediction.
What was it?
Classical physics predicted that any object, any piece of matter, should just constantly radiate away all its energy, all of it.
Wait, so everything should just cool down forever until it hits absolute zero?
Exactly, a universal freeze-out, which, obviously doesn't happen. The theory led to an absurd conclusion. Physics was stuck.
Okay, so the universe isn't freezing. That's good. Enter Max Planck in 1900. He had to fix this, right?
He did. And his solution was, radical. He basically said, forget continuous emission. What if light sources spit out energy in little packets? Equal finite amounts. He called them quanta.
And he came up with that famous equation.
The very one. The energy, let's call it W, of one of these quanta is directly proportional to its frequency, nu. So W equals h times nu. That h is Planck's constant, a fundamental number of the universe.
Okay, so energy comes in packets. But doesn't that immediately sort of reopen the door for the particle idea for light? If it's emitted in chunks.
Precisely. If it starts as a packet, maybe it stays a packet. That led straight to Einstein's 1905 theory of light quanta. De Broglie calls it a reversion to Newton's corpuscular theory, but, updated with Planck's constant.
And this wasn't just theory, there was proof.
Oh, yeah. Pretty quickly, too. The photoelectric effect was huge. Shine light on metal, electrons pop out. But their energy didn't depend on how bright the light was, only on its frequency, its color.
Which makes no sense if light is just a wave, right? A bigger wave should give a bigger push.
Exactly. But it didn't. Only higher frequency packets had more punch. And then came Arthur Compton in 1922.
With X-rays.
Yep, he showed X-rays scatter off electrons like tiny billiard balls colliding. Clear particle behavior. Case closed for particles, you might think.
But physics is never that simple, is it?
Never. Because even with all this proof for light particles, photons, we call them they're off. You still needed the wave theory. You couldn't explain things like interference, diffraction, patterns of light and dark when light bends around corners or goes through slits.
So they were completely stuck. Light acts like a wave here, acts like a particle there. Two totally contradictory models needed at the same time.
It was, as you said, schizophrenic physics. A real crisis.
And this is where de Broglie steps in. He looks at this paradox, looks at Planck's equation, W was high, and sees something deeper.
He really did. He saw that the equation itself was the key. Think about it. W energy, that's a particle concept. It's about impact, mass, motion.
Okay.
But Frequency. That's inherently a wave concept. It's about repetition, periodicity, how often something oscillates.
Right. A single particle doesn't really have a frequency in the same way.
Exactly. De Broglie pointed out a purely particle theory can't even define a frequency. That equation, W-he, forces you to connect the particle world, W and the wave world. They're linked by H.
Wow, okay, so if light needs both concepts.
Then maybe matter does too. That was the leap. If light needs particles and waves, maybe electrons, protons, maybe everything needs particles and waves. Duality isn't just for light, it's universal.
So, his big idea. It is necessary to introduce the corpuscle concept and the wave concept at the same time for everything.
Yes. And the immediate job then became, okay, how did these two things relate for matter? How does the particle's motion connect to its wave's propagation? Find the parallelism.
Let's get into that parallelism. It's where mechanics meets optics, essentially. He starts by saying W has to apply to matter too. Why was he so sure?
It came down to how energy, W, and frequency behave when you, say, switch to a moving reference frame. They transform mathematically in the exact same way according to relativity. That relationship holds true universally. It felt fundamental.
Okay, that makes sense. So starting there, he derived the connection for matter's motion.
He did. The fundamental link became this. A particle with momentum p, that's its mass times its velocity, has an associated wavelength, lambda, given by OE equals h divided by p.
Planck's constant again, linking momentum particle property to wavelength, wave property, that's the translator.
That's the key. And he showed something else really elegant. The speed of the particle itself turns out to be exactly equal to something called the group velocity of its associated wave.
Group velocity, is that just the wave speed?
It's slightly more subtle. If you imagine a packet of waves like a ripple spreading out, the group velocity is the speed of the overall packet, the speed the lump moves at. And that speed matches the particle's speed perfectly.
So the particle and its wave packet are perfectly synchronized. They travel together.
Exactly. And this parallelism revealed something amazing about old physics principles. Fermat's principle, which says light takes the path of least time, and Maupertuis's principle of least action, which governs the path particles take. De Broglie showed they were mathematically the same thing, just expressed in wave language versus particle language.
So the rule for how light travels is basically the same rule for how a particle travels, just translated.
Precisely. The trajectory of the particle is identical to the ray of its associated wave.
Incredible. And this immediately explains something that had puzzled everyone about atoms, right? Those quantum numbers in Bohr's model.
Yes. Why could electrons only be in certain orbits?
Yeah.
Why the whole numbers? It seems so arbitrary.
Bohr just had to put them in by hand, didn't he, to make the model work?
He did. But de Broglie said it's not arbitrary at all. It's just resonance. Think of a violin string. It can only vibrate stably at specific frequencies, whole number multiples of its fundamental tone.
Okay.
Well, for an electron's waves to exist stably around a nucleus in a closed loop, it has to fit perfectly. The wave has to join up with itself smoothly, phase-wise. It can't interfere destructively with itself.
So the condition that the wave fits perfectly around the orbit naturally brings in those whole numbers, just like harmonics on a string.
Exactly. It's a condition for stable standing waves. Suddenly, the quantum numbers weren't mysterious. They were just a consequence of the electron's wave nature.
That's brilliant, but it's still just a theory at this point. A very elegant one, but it needs proof. Hard experimental proof.
Absolutely. Physics demands it. The big test was, can you actually detect these electron waves? Can you make them diffract, like light waves or X-rays?
First step, predict the size. What did de Broglie calculate for a typical electron wavelength?
He worked it out. For electrons accelerated by a voltage, P, the wavelength would be about 12.24 divided by the square root of P times 10 to the minus 8 centimeters.
Okay, the exact number isn't the main thing, it's the scale, right? 10 to the minus 8 centimeters, that's an angstrom.
Tiny. Absolutely minuscule.
Yeah.
But crucially, that's the same order of magnitude as X-rays.
And that matters because
people already knew how to diffract X-rays. You shoot them through a crystal lattice, the regular arrangement of atoms acts like a tiny diffraction grating, and you get interference patterns, the Lau phenomenon.
So the prediction was, if electrons are waves of roughly X-ray size, they should do the exact same thing when fired through a crystal.
Exactly. They should diffract, and the pattern should match the wavelength calculated from HP, or HMV, using the electron's momentum. It was a make-or-break prediction.
If they just scattered randomly, the wave idea was dead.
Pretty much. But the experiments, they were stunningly successful. Davison and Germer in the U.S. were the first. They bounced electrons off a nickel crystal.
And saw.
Diffraction patterns.
Yeah.
Clear evidence of wave interference exactly as predicted using a method just like Lau's for X-rays. Then G.P. Thomson in Scotland confirmed it independently using powders.
Wow. So the waves were real.
They were real. And then there was this really clever experiment by Rupp you mentioned, finding striking.
Yeah, tell us about that one. How did he measure the wavelength directly?
Well, normal diffraction gratings, the kind used for visible light, have lines too far apart for angstrom waves. So Rupp fired the electron beam at the grating at a very shallow glancing angle.
Ah, so from the beam's perspective, the lines look much closer together.
Exactly. It effectively created a grating fine enough to diffract the electrons. And because he knew the actual mechanical spacing of the lines on his grating, he could directly measure the electron wavelength from the diffraction angle.
And it matched de Broglie's equals HP prediction.
Perfectly. It was irrefutable proof. As de Broglie put it, the electron wave is no myth. Wave mechanics was standing on solid experimental ground.
The floodgates must have opened after that.
Completely. De Broglie's idea ignited the development of the full theory of wave mechanics, mainly by Erwin Schrödinger. Later, it was shown to be mathematically equivalent to a different formulation, Heisenberg's matrix mechanics. But it all started with de Broglie's wave-particle insight.
So where did this leave the picture of reality? Is an electron a particle or a wave? What is it?
The new mechanics says, essentially, you have to think about both. A wave must be associated with each corpuscle.
Okay.
And only the study of the wave's propagation will yield information to us on the successive positions of the corpuscle in space. The particle is still there, but its behavior, where it can go, is governed by its wave.
And this is where simple cause and effect, classical determinism, really breaks down, isn't it? Especially when waves interfere.
Totally. When diffraction or interference happens, the wave spreads out. You can no longer say the particle have one specific position at any given moment, like you could classically.
Can you say?
You can only talk about probability. The wave's intensity, the square of its amplitude at any point, tells you the probability of finding the particle there if you were to look.
Like with light. Where the wave is brightest, you're more likely to detect a photon.
Exactly the same idea for matter. The wave dictates the odds. Where the electron wave is strong, you're likely to find the electron. Where it's weak, you probably won't. The wave is a wave of probability.
It's just incredible to think how fast this happened. Under 30 years. From physics being split down the middle, classical particles versus classical waves, to realizing light was weirdly dual, and then de Broglie saying, hold on, maybe everything is dual like that, and then proving it experimentally.
It was a genuine revolution. And that core concept, wave-corpuscle duality, it's not just history. It is the foundation. All of modern physics, quantum mechanics, quantum field theory, particle physics, it's all built on that fundamental duality.
So thinking about this, for you listening, what does this actually mean for how we see the world?
Well, the really mind-bending takeaway, the general view that developed, is that maybe you can't always assign a definite position to a particle before you measure it. It's not just hiding somewhere specific within its wave.
The wave represents the potential for it to be found somewhere.
Sort of. It suggests the wave describes a probability distribution, almost like, well, like possibilities. And maybe it's the act of measurement, the act of looking for the particle, that forces it to choose a location. Before that, maybe it only existed as a spread-out probability dictated by the wave.
So does reality at that fundamental level depend on observation? Does the electron become definite only when we interact with it?
That's the provocative question, isn't it? What does it mean if the wave dictates only chance and location only solidifies when we measure? It certainly challenges our everyday intuition about how reality works.